we go. Okay. So welcome back. We're lucky to have Wang as our next speaker, and he's going to be telling us about hyperbolic and mixed type loops, gas dynamics.
Okay, so first I thank the organizers for this wonderful workshop, and also you see the weather is also very nice. Thank you all for coming. And so for my talk, it's basically kind of a summary of things we did in the past some years. And but the uniform theme here is about hyperbolic or mixed type. Okay, and you will see that they all connect to kind of Euler equations. First, I'm going to give a really brief review for the Euler equation in gas dynamics, especially for this audience. I can go very fast in this part. And then we'll talk about some transonic kind of mixed type problem and past obstacles or in nozzles. And then there is some transonic flow in isometric embedding. So what does that mean? And so in this part, I will give you fluid dynamic formulation about these isometric problems, isometric embedding problem in geometry, and also talk about focus on the hyperbolic problem there. Okay, so first, this again, this is very familiar to the audience here. So gas dynamics, is important. And also, it's the progress in mathematics also kind of based on the demand of this actual technology, like transonic or supersonic flights. And so, well, shockwave, I can show you some pictures. Shockwaves everywhere. We're talking about the singularities here, right? Shockwaves anywhere. So like this, this is the supersonic kind of flight. You can see also you have shock waves here, right? Shock waves and explosion, also shock waves, and this is also high speed bonnet. Also, you see they have shock waves around. And in this picture, I also show you this like air. This is airfoil, right? Airfoil. So airfoil. There are also shock waves around the airfoil. I will come back to this picture in a moment, but here you see that shock waves can be here and also can be on the front here. Okay, so you cannot avoid a shock wave even we have the commercial flights. Well, this is a supernova, and well, volcano, and this is we can the supersonic supersonic flight. You have this sound barrier. We have this, and even water. We have this, right? Yes, yeah. Okay, so equations is also standard here. So what are we talking about here is the compressible Euler equation describing the conservation of mass, momentum, and energy, right? So the full Euler equation is like that here. So we have this also need this equation of state, right? Here, this. Where in the isentropic case, we have this, and we have this gamma law for the pressure, right? So this is all the standard equations. And regarding this Euler equation, first we have the local existence, right? So for example, if the data is smooth, then you can find the local existence of smooth solutions. So there are lots of work starting from Friedrich, Nernst, and so on, the 1D case. And now there are also works for multi-dimensional case on this kind of thing, okay? And so, well, more interesting here is that for this we have formation singularity, right? And first, earlier work is for the multi-dimensional equation was by Sideris. Okay, so he basically says that if you start with C1 data, and then the C1 solution can only exist for a finite time. Okay, so this is actually the first, the very important paper showing that the singularity will form in finite time. But what kind of thing? I mean, an important tool used here is the final propagation speed. But what kind of singularity is what we're talking about here is not that clear. You see, he did not specify what kind of singularity. It turns out this is not an easy task to do. So we see that we have lots of impressive work here. Of course, originally we started from 1D problem, 1D like a Peter Neck, right, and so on, and then continuously we do multi-dimensional cases, right? Even now we have, you see, like this paper. This actually is a book, 800 pages book, to show that shock can actually form for multi-dimensional ordinary equation. Even in this case, they have irrotational flow, right? And then later, we have more work here, right? Continue, and here I quote one result about the formation of shock, like by Burgomaster, Shukoret. And what are they? Okay, they are considering isentropic Euler equations, but with is rotational. So in this work is irrotational, 800 pages something. But here, when you consider rotation with the rotation here, then the analysis becomes also very tricky. And so once a rough statement of this result is that if the for example, for the initial data, if the slope along one direction is quite large, then you can find the shock formation in finite time. Okay, so well, this statement is more complicated than this. Okay, but here I just take a rough one like that. So you see that now this area becomes more and more interesting because new things are found here in the papers. Okay, so we have singularity, and then we have to work on weak solutions. And for the 1D case, and we have a lot. We know it's kind of well known. We have basically we have two framework. One is a small BV in the BV framework, right? And starting from Green scheme, wave front tracking, vanishing viscosity. So Alberto, is here, and also Annex and his collaborators are all working on this, and also here. And then another framework is air infinity, right? Air infinity case, air infinity solution, and also not many people worked on this. But in the air infinity case, we can construct the air infinity weak solution, approximate solution by many different ways, but eventually have to show the convergence. And this has to be done things like a compensated compactness, okay? And Annex just mentioned that. So, Daforma's book actually connected many of these results here. And he said he just finished the 5th edition, right? He just published it. The 5th edition just published. He said this is going to be the last one for him, okay? But that's a good thing. If you look at his books, or the 1st edition is about 300 pages. Now I haven't seen the 5th edition. So each edition, he will add about 100 pages, connecting all, many of the important results. So a good sign is that this area keep going every some years. At least he can add 100 pages. So this is very good. I don't know, the 5th edition, I don't know how many pages. So it's a good thing. But in any case, if you want to see the important results about the consummation, he also connects some of the multidimensional case results here. So this is a good book to see. Of course, Alberto and others also have books. This one he's keep adding the thing. Okay. So multidimensional case, of course, you see is much more difficult, as we all know, and because the generally speaking, the 1D method do not work here, right? And even the space, we don't know. So Jeff Roach had a paper saying that air infinity and the BV are not good space for multidimensional Euler equations, right? So on the other hand, there are lots of works on special cases, right? So for either for like a self-similar or special structures or special reduced system from organ. So also work there. And and the reason, and you can also construct the the infinite many weak solutions using convex integration, right? So Danilis, Kennedy, and also Annex and Min, and they also can construct those infinite many solutions. All right, so one thing you can look at why the multidimensional case is complicated. You see that this is a 2D Riemann problem, 2D mirror. So you see that the waves are really complicated. And we actually don't know if you give the 2D Riemann problem, how many configuration you have. We don't know. And in the beginning, there was a conjecture that you probably have 86, even, and then now reduce, right? It originally said it can reduce to 7 cases, but I still need to verify. So in fact, if you look at those waves here and how to clearly classify, describe the waves, it seems complicated, which is very different from 1D case. Well, for 1D case, the Riemann problem, we know everything basically, right? And then we can use that Riemann problem as a building block to construct the weak solutions, right? So we know even, but multi-D, can you describe this clearly? It's hard to see, looks like, right? So that's the reason, at least one of the reasons, see that the solutions in multidimensional cases could be very complicated, okay? And we don't know much about the structures, so that's make it difficult. Okay, so for a multidimensional problem in general, you're going to you could have this mixed type and also free boundary problems when you consider the multidimensional problems. So this could be come from the Riemann problem, maybe self-similar, shock reflection, transonic flow, multi sheets, and so on, right? So this will give you those all kind of probably mixed type, free boundary. So when you have a mixed type and free boundary, you know it's difficult, right? So and Paulo, the other day he talked about the vortex sheets, right? So this is also an interesting area, very active in reading the vortex sheet, and shock reflection. So you see Misha and Guichang, they also had a lot of things on this, and so we are going to look at this transonic flow here today. Okay. So, well, quick example of this mixed type here. Okay, Trachumi is a very typical type of mixed type problem, but have a fixed boundary, right? This is a fixed boundary here, and I also Kate, and also this other types, right? So this is and we have free boundary here. So this is also mixed type, but if you see that if U bigger than 0 is hyperbolic, less than 0 is elliptic. So U equal to 0 is a boundary, but it's a free boundary. You don't know the solution yet, right? So, and another closely related to the Euler equation mixed type problem is this one. So if you look at the 2D steady potential flow, this is the equation, okay? So phi is a velocity potential, and then the type of this one is like this. So we calculate the eigenvalues, and you see that this equation is hyperbolic if you have a supersonic flow, and it is elliptic is if it's a subsonic flow. So this is in general is true when in gas dynamics, when you have a supersonic flow, the equation type is hyperbolic, and when you have a subsonic flow, the equation type is elliptic. So this generally is true in gas dynamics, especially when you consider, I mean, steady solution. So I mean, this is a problem considered especially in Guichang, in Chen Feldman, and Misha is here. In their book, they study this reaction, and this use the potential flow, and this is one of the typical equations there. So, And so they have a monograph on this. And so when you have a mixed type problem, of course, we know that you have this transition boundary here, and right, and also the boundary is you don't know. So and also you need to deal with other difficulties when you talk about the mixed type and free boundaries, because mixed type means that you have to deal with either both hyperbolic and elliptic, right? So when you have a corner, this gives you trouble here. The corner singularity is also one of the difficulties here. So you have a degenerate PDE and with also corner singularity, okay? And so now let's look at a transonic flow. So transonic flow, what is it? Transonic flow just means that at the same time, you're going to have supersonic, you have a subsonic. So this is a transonic flow problem. And of course, besides this shock waves, and also have other possible singularities. All right. And so now I'll give you two examples here. And so Maha number, here is Maha number. And this is, again, the airfoil, okay? Airfoil. So you see that there is a supersonic bubble here, which is supersonic. But outside this region is subsonic. So that's, for example, you have a commercial flight, right? Although the Maha number, the flight is subsonic. The Maha number is less than 1, so it's subsonic flight. But still around the airfoil, you still have a supersonic bubble and with a shock wave here. So this is called a transonic flow, right? Transonic flow here. And another example is like a nozzle, for example, the engine, right? The aircraft engine. So you have the incoming flow is subsonic, but outgoing is supersonic. You have a transonic shock between. Okay, so this is also a typical example of transonic flows, and they have also free boundaries there. Okay, so look at more closely about this airfoil. So in this picture is actually taken from the airplane flying handbook. So every, I guess, pilot should know this. So this is airfoil, and this picture says that there is a critical speed here. If the flight speed is below this critical speed, then everything around the airfoil is smooth. So that means the speed is subsonic everywhere around the airfoil. Okay, but when the speed is above the critical number, then you start seeing this supersonic region here. So we call the supersonic bubble. The blue part is a supersonic bubble here, and you have shock wave. Okay, so it becomes more complicated. And even higher, then you have more complicated stuff here, right? And so this is mixed type problem. And but we should be careful that if you may think if the speed can keep going, then you know, yes, it's true. If your speed keep going up, you still have this transonic flow, supersonic and subsonic region, transonic flow. But you cannot go higher forever. So at a certain point, for example, like probably around Maha number 4, then it's called a hypersonic. There will be no subsonic region. There will be no subsonic region. Okay, so it's all becomes hypersonic. Then all becomes hyperbolic region. But then I mean they have different problem because the speed is so high, everything changed. So they have different issues there. But here we have this. The issue here is you have the transonic problem. Okay, transonic flow here. All right. Well, we can model this airfoil flow by this 2D Euler for steady and irrotational flow. Okay, so let's say this is the Euler, right? This is a steady Euler, 2D, right? And this is a irrotational condition. So UV are the two components of the velocity x, y, the space variable, and then they have a Bernoulli law. So Bernoulli law says that the density is a function of the speed, q, all right? And well, I mean, first, let's look at the equation here, right? So when you solve this equation here, looks like you have 4, but only 2 are independent together with the Bernoulli law. So for example, we chose the first 2 are the simplest, okay? And then these 2 momentum equations can be considered as entropy equations. So you can derive the momentum equations from the first 2 equations plus the Bernoulli law. Okay, so this is it's good. We have actually automatically have at least two entropy equations if you want to use the first 2. Okay, so this is good. And then let's look at further. And the Bernoulli law can be written this way, and where this Q critical is given by is a constant. Okay, Q, this is constant. And according to the Bernoulli law, right, inside should be positive. Therefore, Q should be less or equal to this one, right? This is the maximum speed. And when you reach the maximum speed, the density is 0. So this is a cavity, okay? So you have the vacuum is a cavity, okay? So when you have that, then it is easier to classify when you have the supersonic flow, when you have the subsonic flow. So for example, when you have a supersonic flow, it means Q bigger than C everywhere. Where on the left side, it just says Q bigger than QCR. So therefore, if Q bigger than Q, this constant, Q critical, then the flow is supersonic, right? Otherwise, this is subsonic. So this is a kind of, okay. So what does that mean? We are looking at the equation. So as we said that if the flow is supersonic, then the equation is hyperbolic. When the flow is subsonic, then the equation is elliptic. Therefore, this 2D steady Euler system is kind of mixed type, elliptic and hyperbolic mixed type. Okay, so this is a mixed type of problem. And there was a beautiful result by Beers-Schiffman in 50s, which says that there is a critical speed, okay? There's a critical speed, Q hat, which is less than Q critical, which means subsonic, okay? There's a subsonic speed, Q hat. If the flight speed is less than this Q hat, then you have smooth subsonic solution. So that means everything around the airfoil is subsonic. And if the speed reaches the Q hat, then you're going to have the sonic points. So this is exactly what that picture says, right? So this is a beautiful result in the sense that it verifies the physics and matches consistent with the physics. And it's a theorem and it describes exactly the physics, okay? So, and then later, of course, there are also more results extending this situation in the 2D case. Okay, there's lots of other results. And recently, we also can look at the 3-dimensional case, but with asymmetric, okay, Euler flow, 3D Euler, but with asymmetric structure. And we also, so when you have the sonic points, then you have the sonic subsonic flow. And so how to construct the solution there. And we can construct solution by the compensated compactness. And so this is what we did some years ago. And so sonic subsonic flow can also be constructed. And how about the transonic flow? Okay, so as we said, if you have the higher speed, then this Q hat, you have the transonic flow. And well, these 2 books, Beers' book and Courant-Philippe, they all mention this transonic flow problem. Of course, in those, in 50s, 60s, they already realize that they are difficult problems, right? But now, still, how many years, 70 years, maybe 60, 70 years now, it's still difficult, okay, still difficult. So, and so, well, we had a brave mathematician, Catherine Morris, who tried this problem, and in her 3 papers, okay? So her main result is this. So as I said, we can consider the first 2 equations. So forget about this R1, R2, set R1, R2 equals 0. So she wants to construct a solution to these 2 equations together with the Bernoulli law. What do we do? How to do it, right? How to do the solution? So her idea is that let's do viscous approximation on the right side. Suppose you can find a good viscous approximation, okay, so that the compensated competitiveness framework can be applied. Then you can take the limit. So when you have the compensated competitiveness framework, you are going to have a strong convergence of a subsequence. Okay, so you can find a subsequence which with strong convergence. So therefore, you can show that she constructed a weak solution of this problem in the implicit problem. But of course, what kind of viscous problem you can propose here so that you can actually apply this compensated competitiveness, okay? So for compensated competitiveness, I will show you more, but there are 2 important estimates you need to achieve. One is that, one is the uniform air infinity bound, okay? A second is, in order to get the strong converge, you need a H-1 competitiveness. So you need 2 things at least, okay? So let's see. So we tried this. So we tried it R1, R2 like that, okay? So this is a viscous approximation we tried, and the theta is a fluid angle, okay? Is a fluid angle here. And this sigma 2 can be, any function satisfy these conditions. So now you need to solve this viscous problem, okay? So the existence, okay, you can do it. But now you want to, first you need to show that the solution of this viscous problem is uniformly bounded with respect to epsilon, right? And also you need to show, H-1 competitiveness. So first, how to get the uniform bound? So the air infinity bound uniformly in epsilon. Well, we still can look at this as, because it's state in 2D. So somehow you can consider one of the, for example, x as time t. So basically you can think this is maybe a 1D problem. Maybe you can think it that way. And although it's still, mixed type, it's not a 1D hyperbolic problem, it's a mixed type, okay? So, so first, of course, this is for the viscous problem with this boundary condition. Then you can find the solution. So how to construct the how to find the uniform bound? One technique you can use is to look at the Riemann invariance. For this system, you can find the Riemann invariance. Okay, so by rewriting this system using the polar coordinates here, you fluid angle, then you can find the Riemann invariance like this. So W plus minus are the 2 Riemann invariants defined by this equation, and then this Riemann invariance satisfy this equation. Okay, so R1, R2, remember, have 2nd order derivatives here, right? So this looks like either you can consider as a parabolic or elliptic is a problem. It doesn't matter. So you're going to use the Riemann. You look at this equation here, and you're going to use the maximum principle to construct the so-called invariant region. So what does that mean? So invariant region means that you find a bounded region on the 5th plane, UV, okay? The region is bounded on the plane UV. And if all the data, whatever initial data, boundary data is in this region, then the solution will stay here forever. That give you our L infinity bound. And if the region, is bounded, right, then it's uniform. So that's the idea of the Riemann region. So you can construct the Riemann region this way. One note is here is that this Riemann region, you need to avoid two things. So one thing is away from the vacuum, which is away from this bigger circle. Okay, this is one. And another one is you need to also away from the origin, which is a stagnation point. But unfortunately, we still cannot avoid this stagnation point. The stagnation point seems hard to avoid at this point. Okay. So with this thing, and then you look at this compensated compactness. Now, first, automatically, we have this uniform bound here. Okay, we have this uniform bound, and by this, and then you need this H minus one compactness. So for this problem, because you have the hyperbolic part, we need infinitely many pairs of the entropy flux. Okay, so you need to plug in and show that this is H minus one compactness. And why? With this thing, we have this this identity, computation identity. Okay, with this computation identity, and this is the is the Young measure associated with this uniform bounded sequence. All right. So the idea is that if this Young measure, associated Young measure, is a Dirac measure, then you're going to have the strong convergence of a subsequence. Okay, but how to show that this Young measure is a Dirac measure? And this identity is true for infinitely many, for any entropy flux pairs. You're going to plug in and then force put into the equation here, right? And then you want to find the unbalance on the both sides, unless this Young measure is a Dirac measure. Okay, so there's a technical part here is that so for what kind of entropy flux pair you need in order to derive the Dirac measure. So this is also a tricky part. And in any case, so we eventually, if we can show that this is a Dirac measure and this is like the service measure, and then so how to construct this entropy plus pair? So it's in fact you have infinitely many, but generated by this solution of the Tricomi equation of this one. Okay, so you have infinitely many, and then plug in, you get the convergence. So you get the strong solution, the weak solution of the strong convergence, and so you have the existence of the weak solution. Okay. So recently, so in that case, we consider gamma is between 1 and 3. So recently, and Guizhang and Ostrom and Schultz, they had a paper try to consider gamma bigger or equal to 3. Okay, this originally seems kind of doable, but now it looks like it's very difficult. Okay, so in this paper, they only consider the gamma equal to 3 and also hyperbolic problem. Okay, so no mixed type. So basically, if the initial data is supersonic and very supersonic, let's say, then the flow will stay supersonic. So you have a hyperbolic problem. And for gamma equal to 3, they can construct. So again, they can construct different kind of, entropy flux pairs, so they can have the convergence. And so again, this is only for gamma equal to 3. So if you want to extend to gamma bigger than 3 or the mixed type problem, at this moment, it's still difficult. And we look at this problem, it seems that we haven't found a uniform way to do it yet. There is you need two things. One is air infinity bound, another one is the H-1 compactness. These two things looks like requires two different things. They are contradicting each other. So we haven't found a good way to resolve this issue yet. Okay. So, but just show you, this is kind of a harder problem here. So some open things that, you know, the transonic flow, the general gas, we don't know. As I said, gamma is bigger than 3, we don't know. And cone and wedge. And in fact, we try to do a cone, but if for infinite cone, that's difficult, okay? For infinite cone, it's very difficult to do. And also evolution equation, that's also at this moment is kind of difficult, okay? So I need to move fast, I think. Transonic in nozzle. Okay, so the compressive flow in nozzle becomes have been extended study in recent years, and for several lots of work on this, so also transonic shocks in nozzles and so on, and contact discontinuity, and so there are many papers on this flow in nozzle. And we consider, for example, a nozzle flow governed by this 2D flow oiler, steady oiler like that, okay? And with ballooning law, again, with ballooning law, and the entropy satisfy this transport type of. So what is the problem we are considering? We are considering a stability problem. So let's see, we start from this flat nozzle, okay? Flat nozzle, and you have an interface here, which is called contact discontinuity. And the upper level is a constant supersonic flow. And here is a constant hyperbolic flow, supersonic flow. So the background solution is a constant mixed type problem here. So this is elliptic, this is hyperbolic, and separated by the contact discontinuity. But now you say that when if you perturb these things a little bit, so original constant, but how about if we make it a low constant here, and also the nozzle will become curved like this, right? So here is still elliptic, it's subsonic. Here is still hyperbolic, but not constant anymore. And here the contact discontinuity also becomes curved, right? And if the perturbation is small, do we have the stability? Okay, so this is the question we are looking at here. And again, look at this. This is a mixed type inside here, and also the incoming flow here. This is the outgoing flow here, right? And so the problem also depends on how do you post the boundary condition here, and also the boundary condition at the exit here. Okay, so in this paper here, we consider the, let's see, right. So at the exit, we put with the boundary condition is the flow angle. So this is the flow angle is prescribed at the exit. Okay, so and I have to say that if you post a more physical one, which is pressure at the exit, which is more physics like that, because it can measure the pressure, right? And things becomes completely different. The technique, the calculation completely different. And so this is something we are, it's our ongoing work. But here, let me show you what we did when we prescribed the fluid angle. So when you have the contact, if you both sides are subsonic, then it was done by Bay and Park. And if it's supersonic, we also did it. Okay, so we consider this mixed type, so subsonic and supersonic. So we did that, and this is the main result here. So this one just said if the perturbation is small, this is what this says, then you can find a solution. You can find a unique solution such that you have the supersonic flow and also separated by the subsonic flow. Okay, separated by the contact discontinuity. So supersonic and subsonic separated by the contact. We satisfy also this stability estimate. Okay, so and also the contact discontinuity also have this estimate here. So this is the stability existence and the stability results of this problem. And the main idea here is that first you need to strengthen the boundaries by using the Euler-Lagrange coordinate transform. But we get everything flat, but now the height of the upper wall is free, okay? Because the mass, incoming mass is not fixed, is not prescribed, okay? So then you still have a free boundary problem, but so you can now you need to handle the second order elliptic equation in the subsonic region and also solve the hyperbolic in the supersonic region. So these two things you have to do it together. You cannot separate. Therefore, you need to develop an iteration scheme and then show the convergence. Okay, so this is what we can. Then eventually you get the solution and also stability estimate, right? So some open problems, and I said that, for example, you have a three-dimensional case. How about the axis symmetrical nozzle, or even the general three-dimensional nozzle, and you know, the pressure condition on the exit, and this is what we are working on. And since many new things looks like different from this, what we have the fluid angle, and also so on. Okay, so many open problems here. And now I have 18 minutes for the look at the isometric embedding problem. Okay, so first isometric embedding is is a classical problem also with new applications, and even in biology. Prudent folding is also okay. So this can date back to Janet, Cartan, and so on. So you see that the work continues even now. Okay, so and it continue on this region. So this is some of the picture. This is a prudent folding. Okay, this is a very fast folding, but how to study the using isometric embedding. Okay, there is interesting connections, but how to exactly use isometric embedding to solve this prudent folding problem is still open. Okay. All right, so a classical result in general is by later gotten by Gunzer. So D-dimensional manifold can be isometrically embedded to Rn Euclidean space, and n is like this. So three-dimensional case, you can embed it to 14-dimensional Euclidean space. But there is a Janita dimension. Okay, so the conjecture is that you should be able to embed a D-dimensional manifold into this dimension. So three-dimensional case, you need to into six-dimensional Euclidean space. Okay, so and two-dimensional case, you should be able to embed it into three-dimensional Euclidean space. And if you do two here, this is 10. Okay, if you have n is bigger, you have more freedom. Okay, so this is the conjecture. You should be able to do it. Okay, every D should be D-dimensional manifold should be embedded in the R capital N. So there are some classical works about an analytical case, and D 2 equal to I will talk about it. But for any higher dimensional, the result is really limited. The reason is that D equal to 3. This is this problem is not elliptic. Okay, not elliptic. And D equal to 4 is not hyperbolic. And D bigger than 4, we don't know what kind of type. Nothing. Okay, so this is. And another difficulty I can show you. So when you D equal to 3, they have 86 equations. And not all of them are independent. And there are papers counting how many independent equations. It looks like their numbers are all different. So we don't know how many. Okay, so this is very complicated. But for D equal to 3, let's see how what can we. The equation looks very simple. So the problem is like this. You have a given metric. You give a metric. You have the first fundamental form, and you want to find a map so that the metric is given. So the map gives you a surface, right? And the metric is given, is preserved. That is, I want a service with a given metric. Can you find such a service? That's it, right? That's the problem. So sometimes you can think this is an inverse problem. Classic series is that if the first fundamental form and the second fundamental form satisfy this Gauss-Quadratic system, then you can find this surface, okay? And even the second form in area infinity, okay? So you have the C11, you have the C11 surface. All right, so here is the equation, the system. So look at the system. L, M, N are related to a second fundamental form, and this gamma here are the Christopher symbol. So if the metric is given, those gamma are given functions. And this is the equation stated, let's say. So this is the Gauss equation, also called the Monge-Ampere constraint. So this is a nonlinear equation part. So all the M and N are non-linear in the two equations, but the nonlinear is here. Kappa is the Gauss curvature. And the Gauss curvature can change sign, all right? So let's see. According to this eigenvalues, the Gauss-Quadratic system is hyperbolic if the Gauss curvature is negative. Otherwise, it's elliptic if you have the positive Gauss curvature and could change sign. Therefore, you have a mixed type, right? If you have the change sign, you have a mixed type. So this mixed type and the other mixed type in transonic flow, are there any connections? Okay, so this is a question we can ask, right? It looks like we didn't know before, but we tried it. We tried to find the connections. So we use this so-called fluid dynamic formulation. So we set this geometry second phenomenon element using the fluid variable, right? Try to connect it with all the equations, right? Then the Gauss-Quadratic system becomes this one. And if you choose the right pressure here, corresponding to this gas, then the ballooning law becomes that. And then you see that if kappa bigger than 0, we know that it is elliptic problem, right? And then the flow here is subsonic, which is also elliptic, right? And if kappa is less than 0, from the calculation, we know it is hyperbolic. The equation is hyperbolic, but the flow is also supersonic from here, from this one. So it looks like under this formulation, the geometry and fluid dynamics match well here. Okay, then you can solve this. In order to solve the geometry problem, you can solve this the fluid dynamic problem, or vice versa, right? Equivalent looks like. Okay, so therefore, if you can find the area infinity solution of this problem, you find the area infinity solution of the Gauss-Quadratic equation, then you find the C11. And so for mixed type problem, you can start from here. But unfortunately, where it is pointed here is that this problem is much harder than the transonic flow problem in gas dynamics. The reason is that the source terms here are way more complicated. And it's very difficult to apply maximum principle. When you do maximum principle, the source terms are very important, especially in their sign, right? So that's very difficult. So for the transonic, it's very difficult. Although we can formulate this way, but it is much harder. All right. So for the positive curvature, positive Gauss curvature, you have elliptic problem. So Benning works. For the negative, well, not so many. And in this review paper, they said it's difficult, and we need to find some kind of global existence. All right. So let's forget about the mixed type for the moment, because we haven't solved the hyperbolic yet, right? Let's look at the hyperbolic problem. So hyperbolic problem, first we want to do the scaling so that the Gauss-Quadratic, this equation of set is global, does not depend on the space variable. This is very important, right? So then let's look at this viscous. So this is a fluid dynamic formulation, and let's look at the viscous case. And because in geometry equations, we don't know, there's no viscous, there's no meaning viscous at all. But we don't know what kind of viscous you can put there to make it work. But now, at least we have the fluid dynamic formulation. Now, this looks like physically, intuitively looks reasonable, viscous. So with this viscous, then we try to do things what we used to do, right? So if we find the uniform estimate first, then do the H minus or convergence, right? H minus competence, so we have the strong convergence, so on. So in that region, we can find the air infinity bound here. But as I said, unfortunately, the coefficients of the Gauss quantity equations play a very important role when you apply the maximum principle. So for this region, for this invariant region, we can only do it for special type of metric. That is for special type of coefficients. And this is corresponding to the catenoid type of surface, okay? This type of surface. So for this method, we can only work for catenoid type, okay? And okay, then we can also, Cristoforo also worked on this same formulation, but she worked in the BV solution case. Okay, so when you have that, and but how to pass the limit? Pass the limit now, in fact, I said L and N are all linear in these two equations, which is good, right? We can pass it and make it a weak solution. But here, how about this, right? For this one, you also, this is nonlinear. Then, unfortunately, we don't have to do complicated compensating competitiveness H1 minus 1 estimate. We can only use, we can use the weakest continuity of 2x2 determinant. So we can only do this. If we can verify the solution satisfies that, and then you have this one, then that's it. Okay, so this part is not that complicated. Okay, you can only do catenoid. How about others? So now let's think about the naive, the original way. So we add the artificial viscosity here, right? But so first in the beginning, we tried this. We didn't know how to do it because from here, you don't know how to find the invariant region. You don't know how to do it. But later, we find that this doesn't work. But if we introduce new variables, we formulate the equation like this, then you can do it. Okay, under this new variable, then you can use the technique, and then we can find the Riemann invariants, and then we can find the invariant region for catenoid type plus anechoic type. Still disappointing. You only add one more type with a different method, but at least we are moving forward, right? So anechoic type, so surface, and you can find this type of invariant region, and this is a anechoic type of surface, and okay, Marshall and Proof also did something related to that, and anechoic it terms a kind of important surface in biology. So this is an interesting paper about property cell. They're talking about geometry and the cell. So so still only two types. Then what to do? Okay, so let's try something else. Now for conservation hyperbolic, we can also use final difference next Friedrich scheme. It's balance law. We can do that. Okay, so then, okay, I'm not going to describe its detail, but then you can work out this type of curvature. For this type of surface, you can do it. Okay, so, well, I mean, when you formulate this problem, you see that this is like the Euler equation with the source term on the right side. But you see that this here. This is like a pressure, it's a negative 1 over rho, which is exactly what we used when we formulate this fluid dynamic formulation. So the Chapman type of gas. So it is not a surprise. Actually, it has to be this way. Like, okay. So well, this is the calculations, and okay, but recently Surani, he worked out the same same kind of weak solution, but for different two type of minimal surface. Okay, so you see that every different method can only push this a little bit further. Okay, so there are still many type of problem surface we haven't covered it yet. Okay, So, for the last few minutes, I'm going to show you what is the smooth. We talk about the weak solution. The smooth isometric bending is equally interesting. In fact, it was the earlier work when people consider this isometric. So you see that they say that, for example, the earlier work shows that for certain cases, you cannot find such smooth isometric embedding. Okay, so basically, like if the Gauss curvature decays like a 1 over root, so root here is the radius. Okay, geometry is radius. Is like a decay like a 1 over root square. Then you don't have this. You cannot find a global smooth isometric embedding. And but now you also propose let's find a sufficient condition, because all the non-existence, there should be something which make it possible, right? So let's find a sufficient condition for the global existence of smooth isometric embedding. Okay. The first groundbreaking work was done by Jiaxin Hong in 1903. So this is really an important paper. So his results show that if the Gauss curvature satisfies this condition, so basically that means that this log here is monotonically decreasing, and the Gauss curvature decays like that, then you have the global existence. Okay, so decays like that is root to the minus to minus a small number gamma. If we just root to the -2, you don't have global existence. But a little bit faster, minus gamma, then you can do it. Okay, but now in this work, first, I mean, this is definitely not the optimal one, right? And second, it needs monotonicity condition. So how about we need to oscillation? We need to include oscillation. So our goal was to relax the decay rate and also allow the oscillation. Okay, so what is our result here? So our result is like this. Okay, so first, regarding the decay part, we only need the interoperability condition. That is, the total curvature is finite. Well, I mean, so the interoperability condition, you can think, could be an optimal condition for regarding decay, right? So this is and another thing, we can include the oscillation part. Okay, this is the oscillation. So A is the oscillation factor, and for the oscillation, we need it to be bounded variation. So variation is a BV, bounded BV. So this is very natural. We needed this. So so looks like we can include the oscillation. Also looks like the optimal decay problem, decay rate like this. And but how do we do this? So how can you make it? Why you can do this? Okay, so well, here is saying that you can include and this is also oscillation. We can include the oscillation part. Okay, this. And also this one says that the PV condition is necessary because otherwise not going to wear post. Okay, something. And so the way to do it, the critical observation is this. So this is the formulation of the Gauss-Kutaisi equation here. And when you consider a simplified case, if the Gauss curve only depends on one variable, then you have ODE. And for the ODE, you can write down the solution. And then you notice that this Riemann invariance W plus Z decays faster than W minus Z. And this is very important. Although it only works at this moment, we saw it in the ODE case, but we like to use it in the PDE case. Okay, very important observation. All right, so now we use the polar coordinates, and the system is like that. Okay, so for this 2x2 system, how can you show this system has a global smooth solution? For hyperbolic thing, you know, we need some kind of dissipation, right? The best you can have is damping, right? If we have damping, you can do it, right? But can we find the damping here? Unfortunately, we cannot find the full damping. We have to dig out that we can only find the partial damping. So let me show you. So we need to introduce new variables here. So under this new variable, we find a partial damping here because this red part has a sign, it's positive, okay? But this is only works for the first equation. There are no damping for the second equation, okay? But as we know that W plus Z decays faster than W minus Z. So we use this property and then we can show that we can control, even though we have a partial damping here, we still can show this system has a global solution with some kind of small data, let's see, right, of course. So in the earlier paper of Jia Hong 1903, he used the comparison principle. But we cannot use comparison principle here because we have the oscillation factor here. We cannot use that, okay? Because it's impossible to construct a barrier function when doing this, okay? So we have to use energy method to do this, okay? And well, I mean, this is energy. So it means here just said we use that partial damping, we can do it. Plus the key observation, okay, we can do it. Okay, so open problems, of course, as I said, we have variable type service. We don't know how to construct their C11 embedding. We don't know. Okay, so this also mixed sign is untouchable there. The mixed sign is really difficult. No results at all at this moment. Higher dimension, as I said, is still basically is completely open. Okay, and many other problems you can see. So okay, I stop here. Yeah.